Hi guys, welcome to module 4.1 of this learner space course on device physics. So in today's module, I'm going to be discussing about diodes. So like I had said last time, we have now covered the basic physics that is involved. Now we are going to actually look into how we are going to apply this into devices. And diode is probably a device that you've seen before. So we're going to just you may have analyzed it from an electrical engineering point of view before or from a circuit point of view before. Now we're just going to analyze it from a device physics point of view. Cool. So, let's start with what is a diode, right? So, just basic introduction. So, we'll talk about the ideal case and then the real life diodes have some non-idealities. So, the ideal case is that it just for a positive voltage across its end, it allows current to flow freely. And if you apply a negative voltage across its end, then it blocks current. So it allows only one type of current, either positively or negatively. And this kind of gives us a clue as to why we care about them. Because depending on the value of some voltage, selectively the current flow is allowed, which means that somewhere or the other, when we are able to make some type of diode, we are getting close to some form of logic because we are able to control the flow of current based on some property of the voltage. Cool. So it also has many practical applications. So things like rectifiers, solar cells, and LEDs. And in many complicated integrated circuits, the diode is used for specific functions, right? So you can look into all of these if you're interested. You can just Google search them or find them on Wikipedia or ChatGPT. Cool. Let's continue with what is real diode is. We spoke about an ideal diode. An ideal diode would just have a, okay, let's show you the ideal diode. It'll just, for any positive voltage, you will have all amounts of current flowing, right? You just slightly positive voltage can allow any amount of current, and negative voltage, no matter how negative you go, the current remains zero. But real diodes don't behave this way. Firstly, real diodes need some amount of threshold voltage for them to actually turn on or like give some meaningful amount of current. And in even if you give them negative voltage, there is a small amount of reverse current that flows, and there is some phenomena called breakdown, which we are not going to study, but you can read about it, where beyond a point, if you apply a current that's really negative, it can cause certain phenomena to occur, which leads to generation of lot of charge carriers. So suddenly the device starts conducting a lot. So you have this thing called breakdown current. If you've heard of a Zener diode, it works on this principle of uh, breakdown current or breakdown voltage, whatever you want to call it. So it works on this concept of breakdown, and we use it as a voltage regulator because if you see, then it allows a large amount of current to flow for at the same voltage. So it can be used in circuits to regulate voltage because no matter how much current you try and force through it, it maintains the same voltage in this region. Yeah, so you can look into that. This is how a real diode works. So I just wanted to point out that it's not like in the real world, the diode is not ideal or perfect, and the threshold voltage beyond which the current starts becoming significant in diodes, or this rise really starts happening, is zero point 0.7 volts for silicon. Yeah, so in many like standard problems when you solve, you can kind of approximate this as the diode being off up to zero point 0.7 volts and then turning on or becoming like a short circuit that allows current to flow freely. Cool. Let's move on. So let's get into the physics of a diode now. So first I want to talk intuitively, and then later we'll get into the talking about it more quantitatively, maybe in terms of band diagrams, Fermi levels, and of course the equations that we've learned so far. So, but it's always good to have the intuition as well, right? So, intuitively, first, let's just, how do you make a diode? So, you just take a wafer of semiconductor silicon, you just dope one side with p-type impurity, other side with n-type impurity. So you have excess of holes on one side, excess of electrons on another side. You can just think of this as you take a p-type material, you take an n-type material, and you just jam them together. Where they meet is what you call the junction. That's why many a times it's called a p-n junction diode. Now, intuitively, what is going to happen when you have a excess of holes on one side and excess of electrons on the other side, and this is something we've even discussed about in the last module, is that these charge carriers undergo a lot of thermal movement, which means that you naturally have a phenomena of diffusion that happens where they move from high concentration to low concentration. Now, what happens because of that is essentially that you have these holes start diffusing from the left to the right. Sorry, I'll just turn on the pointer. I realize it's not on. So the holes start diffusing from the left to the right. Electrons start diffusing from the right to the left because holes have high concentration here and low concentration here. Electrons have high concentration here and low concentration here. Now what happens because of that is that when you have holes diffusing from here to the right, this region, which I have enumerated here, gets depleted of charge carriers because all the holes have diffused from here. So obviously the rightmost region is going to get, rightmost region of this left half is going to start getting depleted first because it's most easy for these holes to go on this side, but slowly some part gets depleted. And similarly, essentially, you know that this p-type material, it's obviously electrically neutral. So when you have these holes that start getting depleted, you have this negative ions that are left behind, right? Because holes are essentially made by this electron, this negative, like this positive hole with a negative ion, and then when that hole is removed from the ion, you are left with the negative ion. Essentially, you can think about it that way. Of course, we think of holes as absences of electrons, but in this terminology, you can talk about it that way. So because this material is initially electrically neutral throughout, and you have positively charged holes jumping from here to here, you you have this uh, region where you have negatively charged ions that are left behind. And symmetrically for electrons, when you have electrons jumping from right to left, you leave positively charged ions behind. So essentially, you are depleting some part near the region from its charge carriers, and what that region is basically called the depletion region. Now, what happens due to this? Initially, what you had was you had this current, this current caused due to diffusion, and initially it was very large current because it's very easy for these to start diffusing. But what starts happening when this depletion region forms is basically that you have, because you have this positive charge here and negative charge here, you start forming an electric field from right to left, which means that for holes to further diffuse from left to right, they have to also start overcoming this electric field. And symmetrically, for electrons to diffuse from right to left, they also have this electric field as a barrier. Cool. So the more depletion you have, the more difficult it is for diffusion to occur. Now, another phenomena occurs which when you start having this depletion region, which is that now we can't get into the specifics of the process, but basically there are many processes that spontaneously create these electron hole pairs or charge carriers in any region of the semiconductor. Now, what happens in that case is essentially that the moment an electron hole pair is created in this depletion region, it gets swept from right. If you talk about positive charge, which is the hole gets swept from right to left. So you start having this current from right to left because of these electron hole pairs getting spontaneously generated and swept from right to left. So you have an initial drift current from left to right because holes are diffusing from left to right and electrons are diffusing from right to left, and obviously the direction of the current is along the movement of the holes and opposite the movement of the electrons. And now you start getting this drift current from left to right. Now, as your depletion region becomes bigger and bigger, your drift current becomes smaller and smaller, right? Because like your it becomes more and more difficult for like those drift carrier this diffusion sorry your diffusion current reduces. I'm sorry if I've like uh, like reverse the two at any point when I was speaking. Diffusion current is due to the diffusion due to the concentration gradient. Drift is due to spontaneous generation and then getting swept by the electric field. Your diffusion current has to overcome the electric field. So at some point, so your diffusion current keeps reducing as the depletion region becomes larger and larger because you have stronger and stronger electric fields, and at some point it becomes equal to the value of drift current, at which point you don't have any net current and your depletion region remains the same after that. So this point would become then the equilibrium of this of this diode. So this is the equilibrium case that actually happens, right? So you have this depletion region basically. So now let's talk about what happens when you actually apply a voltage, right? Because what we've spoken about so far is applicable to a PN junction that you just leave in a cupboard. In real life, the interest of PN junction comes when you are able to apply a voltage. So when you apply a voltage that is positive at P with respect to N, that's called a forward bias, and vice versa is called a reverse bias. So first let's talk about forward bias, right? Cool. So P is kept positive with respect to N, and this favors diffusion over drift. What that means is that essentially when you have a positive voltage here and like here you have positive with respect to negative here, you're creating an electric field from left to right, which is going to counteract this depletion region electric field, and it's going to let your diffusion kind of what do you say, overpower your drift and allow current to flow freely. And the reason it flows freely is that diffusion, when you apply a forward bias, it like very much overwhelms the drift current and it allows this free flow of charge to happen. Now, uh, an objection to this might be that, okay, if you have more diffusion occur, wouldn't that just increase this depletion region and the opposing field and ultimately come to equilibrium again? The reason that that doesn't occur is that when you didn't apply any bias and your holes diffuse to the right and your electrons diffuse to the left, you didn't have anything to replace them, right? But now the carriers are essentially, because of this voltage difference, they are pulled away and you have this circuit that is there to complete. So if this plus like if this hole diffuses from left to right, because of this voltage difference, this more carriers are going to be pulled here to replace those holes. So essentially now, because you have this mechanism due to this positive forward bias to replace these carriers, this depletion region does not further increase, and in fact because you can push carriers in, the depletion region sometimes like the depletion region actually even reduces in size because of this forward bias, because now you can have carriers enter this region. So this is why that objective doesn't that objection doesn't stand, and you can have this free flow of current. Cool. Let's talk about reverse bias, in which this N is kept positive with respect to P, which increases the depletion, because now if you have this positive voltage here, you're going to you're going to have this electric field here, which is further going to push these positive holes away and pull these electrons towards the right, which is further going to increase your depletion region. And the relative strength of drift with respect to diffusion is going to increase, and this is going to make it really hard for current to flow. Now, a common question that people raise at this stage is that why doesn't this simply mean that now you have drift overpowering diffusion, and so you have current in the opposite direction? For this, it's important to revisit how we spoke about where drift comes from, right? So we spoke about how drift comes from this spontaneous generation of charge carriers into this depletion region, and then those charge carriers get swept by this electric field, positive charges in the direction and negative charges opposite to the direction. So yes, when you have this reverse bias, this electric field will undoubtedly become stronger, but this mechanism that generates this charges is still the same. So that mechanism is going to generate the same number of electron hole pairs, which is why your drift current itself is not going to reduce. What's going to happen is that it's going to become harder for your diffusion current to exist because there's a stronger electric field opposing it. So imagine if at equilibrium you had drift current of the order of 10 power minus 6 and diffusion current also of the order 10 power minus 6. Now your drift current, because of this reverse bias, is not going to change. It's still going to be 10 power minus 6, and your diffusion current will reduce to maybe 10 power minus 8. So obviously you're going to have some current from right to left, but this current is still going to be of the order of 10 power minus 6. Whereas when you have the forward bias, you can literally have currents of the order of amperes, which is why that graph makes sense, that your reverse saturation current is very low. The phenomena that occur in breakdown, I'm not going to get into here. You can like read about it separately if you're interested in. So yeah, that's the reverse bias. Cool. So now what I want to do is I want to take you through the band diagram of the diode at equilibrium. So we spoke about some intuition, but now we want to get to the more real stuff like the band diagram. Not the real stuff, but the more mathematical stuff where we start using our equations and all of that. So let's talk about the band diagram, right? So first thing to note is that we will first talk about far away from both the junctions, right? So far away from the junction, the p-type material doesn't know that there is a n-type material, like maybe such a large distance away from it. It doesn't affect it, and vice versa on the n side. So very far from the junction, you don't have any action. All the action happens at the junction. So far from the junction, this on the left, this p-type material does not know that there is some n-type far away. So it behaves exactly like a p-type, and its band diagram is also exactly like a p-type material. And similarly on the right side, it's exactly like a n-type material, and its band diagram is also exactly like a n-type material. You can go back to where we actually discussed band diagrams to figure out like to confirm that this is the band diagram of the p-type and this is the band diagram of the n-type. Of course, orange here is the conduction band, black is the valence band, and the blue is the Fermi level. Now, why have we drawn the Fermi level as flat at equilibrium? Like it's literally from one end to the device to the other, it's completely flat. The reason to have drawn the Fermi level this way is that at equilibrium, this is the only way the Fermi level can exist. And I'll just get into a short explanation on why that is. The reason for that is that the Fermi level dictates that statistically what is your half probability of the state being filled. So if you have like if you have a Fermi level that maybe is high here and then low over here, that means that the states on the left are more filled than the states on the right. And that means you're going to have diffusion from the left to the right, which means you couldn't have had equilibrium, right? So essentially at equilibrium, the statistical analysis of all parts of the device with respect to how many electrons there are should be the same. And since the Fermi level is the measure for that, the Fermi level should be flat. So this is something that we can know about the band diagram, which is that at the extreme left, it's exactly like a p-type, so we draw it like this. At the extreme right, it's exactly like a n-type, so we draw it like this. And the Fermi level is flat throughout. Cool. So let's move on. Uh, I've just picked up this image from somewhere so I don't have to make it myself. But essentially, we saw this part in the last slide. We saw this part also in the last slide. And obviously in the middle, the bands are going to bend because of this electric field uh, that that gets set up, right? Due to this drift and diffusion and all of that. So you're going to sorry, the diffusion and the depletion layer and all this electric field gets set up, and that electric field bridges this band diagram. So if you remember in this band diagram, we are talking about electron energy, and for electric field that's going from right to left, electron energy is going to be highest over here and lowest over here. So it's energy of negative charge. So it's interpreted that way. And like one last thing I want to comment here is that although we spoke about how this is the case very far from the band diagram and then in the middle you have this bridging, we make a sort of mathematical approximation where we say that most of this drop happens in the depletion region, which is the region that is depleted by charges. And on the other side of the depletion region, it behaves like a pure p-type and a pure n-type material. So essentially we are making this approximation that all this action happens in the depletion region. It's not a it's not an obvious approximation, but it is an accurate approximation physically. So that is why we take the liberty of going ahead and making it. Cool. So let's get into actually analyze, like doing some mathematical analysis of this diode at equilibrium, right? So the first thing I want to talk about is equilibrium barrier height. Now, what is this barrier height that I want to talk about, right? So if you saw on the last slide, we had this kind of diagram of P to N where there was this energy barrier from P to N or this energy drop that was occurring. We want to know how much that drop actually occurs, right? So, for figuring this out, we want to like try and figure out the like how this barrier height was actually created, right? So this equilibrium band diagram that we made was made by taking a separate p-type material, like imagine this being a separate p-type material and a separate n-type material, like this is your n-type material, and then you make their Fermi levels align. So how do you make their Fermi levels align? Is that you just pull all the bands of this right side down, and because of this you make this orange Fermi level and this green Fermi level align, and then you say your Fermi level is flat throughout the device, and then you do that bridging in the middle, which we saw on the last slide, and then you call that your band diagram, right? So this is how your band diagram is made. So that energy difference that is created across maybe the conduction band as well as the valence band is essentially due to this like pulling down of this bands to make this Fermi level flat. So that energy difference is precisely the difference between the two Fermi levels. So we are just going to consider them as separate p-type and n-type materials, and we'll then claim that when you make that combined band diagram, the energy difference that you get is simply the energy difference between the Fermi levels. And so you can see that barrier height as this difference in Fermi levels. So if we can calculate this difference in Fermi levels, we can calculate the barrier height. Cool. So let's now go ahead into calculating this difference in Fermi levels. So we are just going to use the formulas that we calculated in this equilibrium carrier statistics video. You can go and watch it. I think it was module 3.2 if I'm not mistaken. So if you don't remember any of these formulas, you can go and watch it. So let's apply it for this p-type material. So we know that the p-type material with respect to the intrinsic concentration, we can write the whole concentration. Now this P naught is just to indicate that it's on the P side, and 0 is just to indicate that it's in equilibrium. So don't get confused by any of this notation. And I actually picked up these formulas from somewhere and they missed this KBT term over here and over here. So I've just shown that I didn't want to write the entire formula again by myself. So I've just shown the correction there. Cool. So we know that based on the expression for the whole concentration with respect to the intrinsic concentration and this Fermi level and intrinsic Fermi level, we can get this expression where you have EFP, which is the Fermi level on the P side, is the intrinsic Fermi level minus KT times the log of your concentration of holes on the P side upon your intrinsic carrier concentration. You can go ahead, go back to those formulas and verify that this is true, or you can just take my word for it right now that it is. Cool. So, of course, we know that all the holes come from the dopants. So, we just write the number of holes as the number of acceptor ions. So, this is the on the left side you have acceptor ions, on the right side you have donor ions. So, this is the expression for EFP. Similarly, you can write this expression for EFN, which is the EI plus KT times log of number of uh, electrons upon the intrinsic concentration, and the electrons on the N side come from nothing but the donor atoms, so the donor ions. So you can write this formula, and of course we knew that the barrier height that we wanted to calculate was this, I'm sorry, was this delta EF naught? So that's just EFN minus EFP. We can do that calculation and see that this is the barrier height. Now, of course, we can also represent this barrier height, which was in the form of energy. And by the way, you can visualize how the bands were pulled down and created this barrier height better in this diagram. So you can write that in terms of energy, but you can also write it in terms of voltage. So charge times voltage gives difference in energy, charge times difference in voltage. So you then get this difference in voltage when you combine these two terms as kBT by Q ln NAND by Ni square. Something quick to note is that we use Q and E interchangeably, small e, to represent the electronic charge, which is 1.6 into 10 raised to minus 19 coulomb. Cool. So this potential due to that energy barrier is called your contact potential. It's called your contact potential. It's because it's caused due to your P and N being brought into contact, or it is also called the built-in voltage. The reason it's called the built-in voltage is because it is built into the device. It's not supplied from some external source. Cool. So that's the built-in voltage. Let's now go into this concept of barrier width, which is that, of course, we spoke about this depletion region. So that depletion region is essentially your barrier, and we want to know the width of that barrier. So indirectly, we basically just want to know the uh, width of the depletion region. So the first thing that we are going to do to calculate this depletion region width is what we call the depletion approximation, which is what we spoke about before. We assume that all this action happens at the depletion region. The electric field occurs only in the depletion region. Sorry, so we essentially assume that all the action happens in the depletion region and this electric field only exists in the depletion region. Uh, yeah, this and everywhere else you don't have any electric field. Now, don't, by the way, don't get confused by this diagram. Don't worry, I'll explain it all in due course of time. So that's this depletion approximation. Uh, so what we essentially now what we need to do is we want to write this electric field. So the way I'm going to do that is I'm going to first convince you of the charge density expression, and then using Gauss's law, I will relate the charge density to the electric field, and then using this electric field we will come up with we will integrate the electric field to come up with another expression for the built-in voltage, except this time we will also have in the variables we will also have our width. So when we equate this to the expression of this built-in voltage that we just calculated, we will get a expression for the width. That is the plan, right, with this derivation that we are doing. Cool. So the now let's get into the charge density, right? So now for charge density is charge per unit volume, of course. Now for this region from uh, 0 to minus xp, which is we are calling the depletion region on the p side, that distance as xp, your entire region is depleted of holes, which means your charge is due to these negative acceptor ions. And that charge density is nothing but minus E times the density of the acceptor ion. So you have this minus E Na as the charge density here, which is shown, this diagram by the way is of charge density. It's shown like this. Secondly, on this side, which is the AND side, you have up to from 0 up to Xn, you have the depletion region. It got completely depleted of its electrons, which means it's only left with positively charged donor ions. And the charge for that is positive E times the density of the donor ions. And everywhere else, you have perfect neutrality because these semiconductor materials are neutral, right? Now, since you had a neutral P and a neutral N and you brought them together, you can't have charge suddenly coming out of nowhere. Charge neutrality also exists, which means that the net positive charge and the net negative charge is the same, which means Na times Xp and Nd times Xn has to be equal. So this is called, this is basically the charge neutrality expression. So now we have the charge density. Next step is we will use Gauss law to calculate the electric field. Cool. So I've presented Gauss law over here, which relates this dE by dx to this charge density. This is called the differential form of Gauss law. You can like if you are familiar with the integral form, you can just look up on the internet how to go from one form to the other. But this is the differential form of Gauss law, and we are just going to apply this equation to write this expression for this electric field, which is essentially this, or from on the left side where x is less than 0, you have this expression. On the right side, you have this expression. And They have also calculated this max value, which is when you put x equal to 0, you get the maximum magnitude of the electric field, which is essentially this expression. The reason we want to calculate this maximum value is that, as I said before, we want to, uh, of course, now we have these variables xp and xn. We also have a relationship between them on the last slide, and we know that xp plus xn is our width, which is what we are actually after right now, which is this barrier width. So we want we want to come up with expression for voltage. Now one way you can get voltage from electric field is you integrate this from 0 minus xp to 0 and this from 0 to xn, and you get the voltage. But a cleaner way of doing that is just recognizing that integration is area under the curve. So we essentially just want this area of this triangle, which is half base times the height. And now base is of course our width, which is xp plus xn, and the height is nothing but this maximum value. So that's why we are interested in the maximum value. So now we're actually going to do that and get our built-in voltage due to this electric field. So we get our built-in voltage by that method like this, and we are able to write our depletion layer width in terms of this built-in voltage by using the relationship between XP and XN. You can like do this algebra by yourself and get this expression for depletion layer width. And obviously we know that this built-in voltage expression is something which we already have access to. So using that, so now basically we have this expression for the depletion layer width, and we can substitute if we want the value of V naught into this, which we had already calculated. Cool. So I want to now remark a bit I want to get into talking about forward bias. Before that, I want to remark a little bit about something that some quantity in equilibrium. What I want to remark on is that this is your P side. One second. This is your P side. This is your N side. I want to talk about the concentration of the holes at the edge of the junction on the N side. And we can get this concentration by using the formula Np equal to Ni square. We know that N, or the number of electrons, is equal to the number of donor impurities on this side. So from that we get the expression for P at the n side at equilibrium, which is what this notation is, Pn naught, which means the number of holes on the n side edge at equilibrium as this. Uh, for now, we're not doing anything with this information, but what I want, the reason we care about this is that the current from left to right, which we would get when we apply a forward bias, so the current that we want is like a big part of that current is diffusions of the holes from the left side to the right side. So when we talk about the current that's made by this diffusion, the whole concentration at this edge becomes important, and we're going to see how this changes when we apply the forward bias, which is why I wanted to talk about it in equilibrium. Another thing to note is that the at equilibrium over here, this diffusion and drift are equal. You have diffusion towards the right and drift towards the left. They equal and opposite, and they cancel each other out. Yeah. So now I want to get into what happens when we apply a forward bias. Cool. Let's analyze now what happens when we go into forward bias. So uh, again, just don't get intimidated again by this diagram. We'll analyze it step by step. So the first thing that I want to note in this is that your extreme right is still going to behave like an N-type substance, and your extreme left is still going to behave like a P-type substance. But because you're applying this forward bias, and that is denoted by this V forward, uh, your your net difference of potential from the left to the right is going to reduce, because of course the energy of the electrons on the right hand side is going to be raised by this forward potential. A way to think about that is that applying a positive voltage on the P side is as good as applying a negative voltage on the N side. Electrons being a negatively charged carrier, their energy is going to increase if you apply a negative voltage, which is why the bands on the right are going to be pushed up. Now, we are left with an issue when this happens, which is that when we have to compensate, like this difference between this top end on the left and top end of the right increases by Vf, but we still want that at the far ends, which is the far right, it still looks like a N type material, and at the far left, it still looks like a P type material. The issue we are having is that for this to be true, the Fermi level cannot be flat. Because if the Fermi level is flat, which is what we saw earlier, you need the difference between the tops on the two sides to be equal to the contact potential V naught. So when we are trying to balance this out, we run into this issue, and this is not the origin of the way we compensate for this issue, but a consequence of the way, like the reason we run into this issue and a consequence for the way we run into this issue is that we don't have an equilibrium situation anymore. The very concept of a Fermi level was defined for equilibrium, and we don't have equilibrium situation anymore. So we cannot have this concept of Fermi level in its original form anymore. And the way we solve this, I will first tell you what we do, and then I will justify why we do it. So what we do to solve this issue is we split the Fermi level into an electron Fermi level and a hole Fermi level as two separate entities, and we call both these Fermi levels quasi Fermi levels. So now you can notice that when we do this splitting of Fermi levels, our issue kinda gets resolved, because we can have these two different Fermi levels, and we can have V naught minus Vf as the energy gap between the P side and the N side. But at the extreme right and extreme left, it still looks like a normal N type material and a normal P type material. So this is kind of our motivation for why we split the Fermi levels. Now I'll just talk about why it is justified to do this. Cool. So one thing that's important to understand is that the Fermi level is a mathematical tool that is used to analyze equilibrium carrier concentration. Now, when we apply a bias, we are no longer operating in equilibrium, because the bias is going to push holes from the left to the right, which means that you're going to have excess of holes on the right, and the number of electrons on the right is gonna largely stay the same, because that's determined by a number of charge carriers. So overall, of course, we are not talking about the depletion region, but beyond the depletion region, when holes actually diffuse into the right. So overall, your bias is going to raise the concentration beyond this thermal equilibrium level, which means that the Fermi level can no longer be used in its original form to analyze this equilibrium carrier concentration. This is why we introduced the concept of quasi-Fermi levels, and the assumption that we make when we introduce this concept is called quasi-equilibrium, which is that the bands internally reach equilibrium, but there is not a net equilibrium. Now, what we mean by this situation is that the conduction band itself is in equilibrium with itself, the valence band is in equilibrium with itself, but they are not in equilibrium with each other. So the reason for this is that the scattering and thermal effects that happen in these bands internally happen at such fast rates that they can attain equilibrium easily. But there is not enough time for them to attain equilibrium with each other. What this means is that your conduction band is in equilibrium, your valence band is in equilibrium, but they're not in equilibrium with each other. So now, of course, the conduction band is what describes the electrons as a carrier, and the valence band is what describes the holes as a carrier. So what this essentially leads to is that we can treat the electrons separately in the conduction band as if they were in equilibrium, and we can treat the holes separately in the valence band as if they are in equilibrium. So, which is why we have a separate Fermi level for the electrons and the holes. And if we keep this difference between these Fermi levels as exactly the forward voltage that we are applying, we are able to actually solve this issue that we were initially having of not being able to have this V naught minus Vf difference, as well as have the left and right side look purely as P and N type respectively. Because when we keep this distance exactly difference exactly as Vf, this issue gets solved. Another way to look at this intuitively, I'm just trying to give intuitive explanations for this because this is kind of the crucial step when we introduce biases. The other way you can look at this is that with a single Fermi level, there is a trade-off between the electron and hole concentration, and that is why you have thermal equilibrium. If you raise the Fermi level, you get electrons but you lose holes. If you lower the Fermi level, you get holes but you lose electrons. Now what is happening in this case is that your overall number of carriers, both electrons and holes, are increasing at a particular point. They're increasing from the thermal equilibrium because you're having diffusion from the left to the right. So on the right you had a given number of electrons, but you're having an additional number of holes. So now this trade-off that was there between electrons and holes can no longer explain what their concentration. So you need to introduce separate Fermi levels for electrons and holes to actually deal with this situation. Cool. So yeah, that's the justification that I wanted to give with respect to the Fermi levels. The next thing is like, how do we use these Fermi levels? What do I even mean when I say that I have this quasi Fermi level of electron Fn and quasi Fermi level of hole Fp? What I mean by this is that in all the formulas which we essentially derived in the equilibrium carrier statistics, uh, we instead of using the Fermi level, we will use the quasi Fermi level. So if we are talking about the concentration of electrons, we will use the quasi Fermi level of electrons. If we are talking about the concentration of holes, we'll use the quasi-Fermi level of holes. So mathematically, we can continue to use the concept of a Fermi level and plug it into our previous formulas by introducing these quasi-Fermi levels. So that is how we actually go ahead and use it. Now, the next thing I want to do is I want to talk about this like this uh, sorry, the electron, uh, just give me a second. I want to talk about the hole concentration at this edge because that's what we spoke about as being crucial to talk with respect to the diffusion current. Now, the hole concentration at this edge, if we use the formula that we generated in the basically in the uh, carrier concentration video, this formula was there where it's dependent on this exponential of the difference between the valence band and the Fermi level. Now the Fermi level here is replaced by this quasi Fermi level. But you can see that this Fermi level Fp is Vf less than the original Fermi level of the device. The difference is Vf, which means, by the way, there is a typo here in the source. this particular FP is supposed to be EF, which is the original Fermi level. Cool. So just note that typo. So if we replace FP as EF minus VF, which is the difference with respect to the original Fermi level, we can get this expression for the whole concentration at the edge. And if you notice, this part of the expression is nothing but the equilibrium. When we had the valence band at equilibrium, uh, but the what do you say, the this is the factor that gets multiplied with respect to the equilibrium concentration. So because of this splitting, you can go through the steps and see that your concentration becomes raised by this exponential factor dependent on the bias that you put. So your Pxn by Pn at equilibrium becomes exponentially dependent on Vf. So if you increase Vf by some small quantity, your net whole concentration at this edge will increase by a very large quantity, and that's because of this Fermi level splitting that actually has occurred. So yeah. Uh, Another way that you can look at this, if I my explanation was confusing, is that you can look at uh, EV. Uh, you can look at EV in the non-equilibrium forward bias case as being raised up by VF, and your FP being equal to your initial Fermi level, and everything else was just raised up. So what I initially spoke about was looking at the left side as being raised down, but you can also see the right side as being raised up. It does not make a difference. In which case your FP can simply be replaced by EF over here, and if you view it in that sense, then this is not a typo. Your FP can be replaced by VF, and your EV is just EV naught, your original valence band, plus QVF, because it got raised by this value VF. And since FP and the original Fermi level are the same, you can replace that and you can take this QVF outside the exponential and get this term. So essentially, the way you look at it can change the interpretation, but the final explanation that you get is that your by this factor the whole concentration over here increases, which is very obvious because when you apply forward bias, you're going to have a lot of holes diffusing onto this side. Uh, Another consequence of this is that your diffusion current very much overwhelms your drift current, and now we're like in the subsequent slides, we're going to start seeing how we can actually start writing the expressions for this current. Cool. I'm sorry if that last slide was a bit much to take. I'm sorry if I made any like I misspoke or anything while saying that. You can just go through it again, and the basic concept is just that these Fermi levels split and that change our calculations. The same analysis we do for the holes on the N side, we can do for these electrons diffusing onto the P side, and we get this expression also as being equal to this exponential term. Now, we've done this calculations, we've spoken about this quasi-Fermi levels and all of that. That is fine. But what are we actually trying to get at, right? What we are trying to get at is that when you apply this forward bias, the reason you get this current is because in this N-type material, you're injecting minority carriers. For the N-type material, the holes are called minority carriers. You're injecting minority carriers from the left to the right because they are rising from their equilibrium value. And for this type, N-type material, you are injecting again minority, and for this P-type material, you are again injecting minority P-type carriers from the right to the left. So when you're injecting these carriers are going to undergo diffusion into this side. That is what is going to correspond to creating your current. So when you have injection of carriers from minority carriers, that constitutes a current, and that is what we are trying to calculate. So obviously this injection is over and above equilibrium. So if we take the difference of Pxn and Pn naught, we get the number of carriers we are injecting. And if you're injecting charge onto some material and that charge starts diffusing, that starts constituting a current. And that is how, like, viewing it this way is how we are going to try and derive this current on due to the forward bias in the diode. So far, I hope you're with me. If you're not, just take a bit and think about it. I know this explanation has gotten a bit long, but you're essentially having carriers being injected. You have this holes at the n type edge which are over and above equilibrium, which is basically like, due to diffusion, holes are being injected into this n type material, and due to their diffusion in this n type material, you're going to have a current, and that is the current that we are trying to calculate. Yeah, I hope all of that is clear. So you just have, because of this forward bias, you're splitting of Fermi levels, which leads to this phenomena called minority carrier injection. And the amount that gets injected is given by this expression. Cool. Moving on. Okay, so now we are going to try to calculate the diffusion current due to these excess holes on the N side. Now, you might remember this expression. If you don't, just go back and check it out, which is basically this continuity equation, which is that your number of holes changing, rate of change of number of holes can be written in terms of generation, recombination, and current. These three factors, not current, but gradient of current, or how current is changing with respect to distance. So in a given volume, these are the three ways that your number of holes per unit time changes. Now, of course, your number of holes per unit time is not going to change once you have this quasi-equilibrium in your diode. So this term is zero. You don't have any process that leads to generation, which basically means that this leads to this equation where this is your gradient of the current, and this is your rate of recombination. Now, so this is the first equation that we are going to use. The second equation that we'll use is simply the whole current in terms of drift and diffusion. Now we are going to assume that diffusion dominates over drift. So we are just going to write the diffusion current, which is nothing but Q times this constant times the gradient of charges. So what we are essentially trying to do is just equate, differentiate this, and we have two expressions for dj by dx. We'll just try to equate those two expressions and get some get an expression for the whole concentration as a function of x. Remember, what we did in the last slide was just the whole concentration at the edge of the n side of the material. Now, due to diffusion, that whole concentration is going to reduce. So once we get the whole concentration as a function of x, we can then use dp by dx to calculate this j, and we can know this whole diffusion current. So cool. This is why we come up with this second expression for dj by dx. Now we want to write recombination. We know that this recombination can be written as delta p by tau. This is something that we again saw when we spoke about recombination. So we are going to write that. So we just equated both the dj by dx, and now we get this differential equation of p of x, which is the whole concentration as a function of x. Now we just define this diffuse some new quantity called diffusion length as under root d times tau, and we get that as LP square. This is not an important part, it's just something that's done by convention. Now we can define P of x minus the equilibrium value of P as the excess concentration. This double, when we take the double derivative of on both sides, we can replace this expression by this expression since this is a constant, and we get this differential equation with respect to the excess concentration. So remember, what we are trying to do is we are trying to calculate the excess concentration as a function of the distance, and yeah, the way we calculate it as a function, what we do by calculating it as a function of the distance is, once we know the excess concentration as a function of the distance, we can use that to calculate the whole diffusion current. So the general solution of that equation for x greater than xn is given by this. You can just think of xn as some type of shift of origin. This is just your standard calculus. Now, obviously, okay. So the assumption that we are taking is that we have a long diode. So if we have a lot of diffusion, then we can just assume that the length of the diode is enough that the diffusion eventually dies out. So we can essentially, just assuming a long diode, just take x tending to infinity, and since that quantity should be equal to 0 because your diffusion dies out, and this would take that quantity to infinity, the value of b should be 0. And the second boundary condition that we have is that at x equal to xn, this delta px is given by our delta pxn quantity, which we defined in which we derived in the previous slide with respect to that exponential e power qvf by kbt minus 1 dependence. So this is how we get this whole concentration as a function of x. We have the whole concentration at the edge, but now we also have it as a function of x. If you want, you can also write the total whole concentration from this by just adding the equilibrium concentration. Now comes the reason we were doing all of this, which was that we want to write this whole diffusion current at the N side, which is how much current is caused by diffusion of holes into the N side. And for that, we just use the standard formula of diffusion current, which we had seen before. We need to substitute dP by dx. We can substitute this dP by dx we can like differentiate the expression for dP by dx from the last slide, and we can substitute that into this, and using that we finally get this expression for the whole current. Uh, Now, using this, we get this is the general expression for the whole current. We can also calculate this whole diffusion current at the edge of the depletion region, which is at x equal to xn, and we get this expression where we put x equal to xn, and we can now expand out our delta p xn. I've just like screenshotted this formula from somewhere else. They have used this variable name as lambda instead of L, but otherwise it's just delta p xn. And remember, delta p xn is p at n naught times e power qvf by kbt minus 1. This is something which we had calculated before, and we can write p at n naught as ni square by nd, which is something which we also saw before. So we have this expression of diffusion current at xn. Uh, Now we are going to use this expression to calculate the total current in the diode, which is our ultimate goal, which is that we want to be able to calculate this total current as a function of the bias voltage in the diode, because once we have done this, our characterization of the diode would be complete. Cool. So this is our expression for the diffusion current at Xn, right? Cool. So now we want to talk about this total diffusion current. So just because just the way you have diffusion current at Xn of holes, you also have diffusion current at Xp of electrons, and this will have an identically similar expression. Cool. So how do we have the diffusion current of electrons here, and we have the diffusion current of holes here? How can we possibly use these two quantities to get the net current that's flowing, right? Because net current, like to add up currents, you need them to be at the same position. You need to consider diffusion current as well as drift current and all to get the net current. Cool. So I'll just break this problem down a bit. First remark that I want to make is that the total current is constant throughout the device. And this is something that you can see from this continuity, which is that you don't have generation, recombination, or all of this happening on net in the device. You might be having it in some parts of the device, but on net you don't have any generation, you don't have any recombination, and you don't have any change of dn by dt. So which means that J is constant, the gradient of J is 0, which means that J is constant throughout the device. So the first part that we justify is that the net current is constant throughout the device. So what that means is that if I can write the net current at any one point, that is same as the net current everywhere else. So that is the first step of progress. The second step of so now what I'm going to try and claim is that I will try and write the net current at this point xp, and that will be equal to my net current anywhere in the device. Now, how do I write the net current at xp? One is I have this diffusion current J and diffusion, which is due to the electrons diffusing into the p side, which is this expression right here. So electrons diffuse from right to left, which corresponds to a current from left to right. So that is one component. The next assumption we take is that diffusion dominates over drift. So we don't need to consider drift in this expression. So I don't need to consider drift of either electrons or holes. Which means I simply need to add this to the diffusion of the holes. Now, the issue is that I calculated the diffusion of holes at xn. I did not calculate them at xp. So how can I know what the diffusion current of hole at xp will be? So for that, I will again ask you to refer to this formula. We know that in this region you don't have any generation, you don't have any recombination, and your P as a function of time is not changing when you have this quasi equilibrium situation. What that means is that your gradient of Jp in this region, net Jp, which includes diffusion and drift, but we are neglecting drift right now, does not change. What that means is that your gradient of your diffusion of your net current, and therefore your diffusion current is zero, which means your diffusion current is constant throughout here. Now obviously your diffusion current reduces here, and the way we are able to get over that, get away with that, is that here we are not in this region we are not claiming that your drift current is negligible. We are only making that claim over here, that here your diffusion dominates over your drift. So your net Jp gradient can still be zero while your Jp falls here. But here, since diffusion dominates over drift, your Jp gradient being zero means that your diffusion current has to be constant, which means that your diffusion current of holes at xp is at xn is exactly same as your diffusion current of holes at xp, which means that now you have the diffusion current of holes at xp, you have the diffusion current of electrons at xp. At xp you are saying that the drift is negligible compared to the diffusion, so the net current at xp is just the sum of the diffusion of electrons and the diffusion of holes. And given that we know the net current at XP, we know the net current everywhere throughout the device because the net current in the device is constant. I hope you are following that logic. If it got a bit confusing, I think I was clear enough, but it may just have been a bit fast, so you can maybe just rewatch uh, this explanation. So the final point that we are trying to make is that the net current in the device is just the sum of this quantity and this quantity. And when we actually go ahead and sum it up, we get this expression times e power qv by kbt minus 1. And this entire expression is a constant. We can call that constant J naught. So we get this J naught e power qv by kbt minus 1 as our net current in the device. So this is a complete characterization of the diode. We know that what voltage we apply will result in what current. Now, something that like some gut checks which we can do. One is that since it varies exponentially with voltage, we can easily get this part of our IV. Oh, sorry, I'm bad at drawing. I think I'll just use the marker. But if this is our I, this is our V, then this part of our IV curve makes sense with this exponential. Second thing that we can see, which is the reverse saturation current, which is that when V tends to minus infinity, this whole expression just tends to minus J naught. So you just have that flat line here. Obviously, we've not considered any breakdown, so this formula does not encapsulate the breakdown. But we can see that this formula makes intuitive sense with respect to the diode. For negative values of V, this is very low in magnitude, and for positive values of V, you have a high magnitude positive current, which is what we want. So you can see that this fits the characteristics of the diode that we previously discussed, and this is the net expression of current in the diode. So we have done like a proper analysis, device analysis of the diode, and now we know that when we apply a given voltage to a diode, what current we will get out of it. Cool. So that brings us to an end of this module. I'm sorry that was a long module. It's just that when you are discussing devices, you like want to be thorough in like covering all bases. So yeah, in terms of the I don't think I like covered a lot of new concepts, but it was more of application of all the equations which we learned last time, which you would have seen at this end of this module. And yes, we did talk about this new thing called quasi-Fermi levels, which we uh, invoke when we don't have equilibrium, but we can have something called quasi-equilibrium. So the key takeaways from this module, how a diode works. I think you can fairly well claim that you now know how a diode works. We learned the band diagram of a diode. We learned about quasi-Fermi levels, and finally we derived the expression of current in a diode with respect to the bias voltage, and like we did it from the fundamental physics of the situation. Cool. Finally, in the next module, I want to cover MOS devices, and that kind of brings us towards talking about the MOSFET and how the MOSFET works. So, yeah, I would like try to keep that the last module of the course. So yeah, hope to see you guys there. Sorry, this was a long one. Maybe you can watch it in breaks. Or like rewatch certain parts that are unclear. I hope to see you guys in the next module. Bye.